let's say that you have ran a regression and you have gotten an estimate, a coefficient, of either the intercept or a slope, and this is, for example, 90, just to have something to calculate with. And along with this coefficient, you get the standard error of this coefficient estimate, because this is a random variable, because every time that you gather new data, you would probably get a different estimate of this coefficient. So if you have a lot of data and thus you have a lot of degrees of freedom, then you can assume that this beta hat, this coefficient estimate, it follows a normal distribution. Okay, so this coefficient is really just a random draw from this distribution. And if we have a prior hypothesis, for example, our hypothesis is that the true beta from which this sample beta is drawn from is equal to 100. And you see that the difference between the beta hat, which is 90, and the null hypothesis is -10, right? So this is a distance of -10. The problem is this a large gap or a small gap? And this is where the standard error of this coefficient comes in handy, because if we assume that the standard error, which is 5, is true, or is an unbiased estimate of the true sample distribution of beta hat, then we can draw this normal distribution around the null hypothesis. And the benefit of doing this is that we can calculate with probabilities. So now we can, instead of measuring this distance in units, we can measure this distance in standard deviations. And we have a distance of -10, and the standard error is 5. So we see that we need 2 standard errors to cover this distance. So this is coincidentally equal to the t statistic, which is just the sample beta minus the null hypothesis beta divided by the standard error of the sample beta. In our case, this is equal to 90 minus 100 divided by 5, which is -10 divided by 5, which is -2. So the distance between the sample beta and our null hypothesis beta is -2 standard errors. So the t value gives you the distance in standard errors. And the benefit of this is that now we can calculate the p-value, which is the probability of getting something more extreme just at random, given that the sample distribution is centered at the null hypothesis and that the standard error is actually correct. And in our case, we have a t-value equal to -2, and as such, we can use the z-table here if we assume that we have over 200 degrees of freedom in our model. So that would be the number of data points minus the coefficients in the model. We can assume the the normal distribution. And what we do here is that we found a t-value of -2, and thus we look at the first column here and we go to -2 and we have -2.0, and the third digit is also 0, so we end up here of 0.0228, which is the left tail probability. So this table, this z-table, gives you only the left tail probability given a value of z. If you would like to have the right tail probability, you could just find the left tail probability of the negative of the z statistic, and you would get the right tail probability. But let's focus on the left tail probability here, and we got, let's see, here a number, a probability of 0.0228. So this area here, the left tail probability is 0.0228. In our case, we have a two-sided test because this null hypothesis, this null hypothesis is just a point. So if we are interested in answering the question, what is the probability of getting something more extreme to both sides than this t-value of -2, we also have to go here to +2. Okay, so this is t-value equals +2. So this is t-value equals -2, and we would have to consider the probability of the right tail of 0.0228, and why is the left tail probability equal to the right tail probability if we go equally far out here? It's because the normal distribution is symmetric. So the p-value of this two-sided test equals the probability of the left tail plus the probability of the right tail, which is equal to 0.0228 times 2, and this would be equal to 0.0456. So the probability of getting a more extreme t-value than -2 or +2 is 0.0456, given that this null hypothesis is true, and given that the standard error of the sample distribution is true. So this is just 4.56%. In the case that we have a one-sided test, then we could think about the null hypothesis as a range of numbers. So if the null hypothesis here is that the beta is greater than or equal to 100, then all of this would fall in the category of, or the range of, the null hypothesis. And you would only reject the null hypothesis if you miss the null hypothesis by a statistically significant amount, or distance as measured by the t-value. So if you have 90 here, and this is your sample from your regression, then you could think of the exact same normal distribution, and here you would only care about the one-sided tail. Okay, so this would then be or give you a p-value of 0.0228. So this would be the probability of, at random, getting something more extreme than you actually observed. If, however, you are considering the right tail, that you have the null hypothesis range here. So this is, for example, 100. This would be H naught, is that the true beta is lower than or equal to 100. Then you would try to find the right tail probability here by use of the table. However, this table only gives you the left hand side of or the left tail probability, which means that you would have to find the left tail probability by changing the sign of the t value. So for example, if we got a result of 110, and that would be 2 standard deviations above the null hypothesis, so the t value would be +2, then you could find the right tail probability by looking at the z value of -2 here, and find the tail probability of the left tail, which is equal to the right tail probability for a t value or a z value of the opposite sign. So this is how you find the p-value for a two-sided and the one-sided hypothesis test.